Hello and welcome to this video. Last time we saw the concept of maxima and minima, and if you remember I said it has many applications in physics as well as engineering. So today we'll look at a simple example of the problem, of the concept. So let's just dive straight into the example. So let's say you're working in some industry and you have a piece of cardboard. So it's a rectangular piece of cardboard. Okay, so excuse my drawing, but okay, so you have this piece of cardboard and there's a constraint on it. So that means you need to make this cardboard which has a perimeter. So the perimeter of this cardboard, you need it to be 100 centimeters, let's say. So maybe you're making some kind of packaging box and you need the perimeter to be 100 centimeters. And now to fit this, the product, let's say, into this, you want to find what is the maximum area I can get from this by changing the sides of this rectangle, keeping the perimeter constant, of course, at 100 centimeters. What is the maximum area I can get of this rectangle? So this is x, and since this is a rectangle, opposite sides are congruent. So let's try to solve this problem. So we have, importantly, so this is always called the constraint, and such problems are called optimization problems. So here you can see we want to optimize the amount of area we are getting out of this cardboard. So this is the constraint. Okay, and this is important. You need a constraint in such optimization problems. So here, since we have this constraint, let's just write down what this means mathematically. So the perimeter of the rectangle is just the sum of all the sides. So that's 2 times x plus y, and that will be equal to 100. So from here we see that x plus y is equal to 50, and so let's isolate y. Y must be equal to 50 minus x. So we have here an important equation which we will be using soon. Now we need to find the area, since we are looking for the maximum amount of area we can get. Okay, so the area of a rectangle is, so let me just write area A. The area is equal to the product of the length and breadth. So in this case, x multiplied by y. Now x I'm going to rewrite as it is, and y, as you can see from this equation, I'm going to write it as 50 minus x. And you know, the reason I have done this, and I have not just left it as y, is that all the functions we look at currently, so at college level, high school level, are functions of one variable and not two. So here area is a variable of one dependent variable and one independent variable. So for example, we look at functions of the form y is equal to f of x. So maybe y is equal to x squared or something like that, sine x. But we don't look at functions like maybe sine x multiplied by z. We don't look at such functions. These we will see later on. As of now, we are just looking at single variable functions. So there's only one dependent variable, and so in order to eliminate the second variable, we have to rewrite it in terms of the first variable. So as you can see, now this equation is of the form y is equal to f of x, and this is actually the main function, the main use of the constraint is to eliminate one of the variables. Okay, so let's continue. So the area is equal to x times, so you can just rewrite this 50x minus x square. And as if you remember last time, the way we found the maxima and minima was to take the derivative of the function and set it equal to 0, and then find the x values for which that statement holds. So let's do the same here. we take the derivative with respect to x, of course, since this function is a function of x. So that is equal to the derivative with respect to x of 50x minus x square. And this is a pretty simple derivative. So that's just equal to 50 and minus 2x. Okay, so now we got that the area, the derivative of the area, so how the area changes with respect to x is equal to this. So now keep this equation in mind and I'll come back. Okay, now so we have to set this equal to 0. That gives us 50 minus 2x is equal to 0. And remember that the concept behind this is what we saw last time. Basically the function can attain a maximum or a minimum only when the derivative is 0. So that gives us x is equal to 50 by 2, that is equal to 25. So we found that x is equal to 25, what was the unit? Centimeters. Now let's see whether this is a maximum or a minimum, because remember that when you set the derivative equal to 0, you get a maximum or a minimum and you need to check whether it's one of those, which one of those it is actually. So the area was equal to x times y, and since y is 50 minus x, that's 50x minus x square. Plugging in x is equal to 25, we get 50 multiplied by 25 minus 25 square. And that's just 25 times 50 minus 25. This is equal to 25, so we have 25 square, that is equal to 625 centimeter square, since this is area. Now this definitely must be a maximum. So this must be a maximum because let's say you plug in any other number other than 25 centimeters. So let's say you plug in 10, you would get 500 minus 100, that was 400, which is less than this. So this cannot be the minimum, this must be the maximum. So we have just found that with this constraint, so if you have the perimeter equal to 100, then the maximum area you can get out of that figure must be 625 centimeters square. And also notice that the reason I gave this constraint is so you realize that if you ever have a constraint on the perimeter and you want to optimize the area, you will get a square. Notice that if x is equal to 25 centimeters, y, which is equal to 50 minus x, will also be equal to 25 centimeters. And so this figure actually is a square if you want to optimize the area with the perimeter fixed. And so this is a useful observation that we can actually gain from this example. Hopefully you all enjoyed this problem and learned something from it. We will be continuing with the series of derivation in the next video. Bye for now.